Okay, right? So this is the momentum thickness. This is the boundary layer right here. So experimentally, when things become turbulent, we can still do these measurements. And that's sort of where this idea comes from. Because remember, for the internal flows, right? It's going to happen something like this. Okay, so this is the turbulent, and we just see that it's getting right close to the wall. It has to really get down to zero really quickly. And then there's sort of this area right here when it's still not exactly U infinity, but there's still slow growth. So that's that's really the idea of turbulent boundary layers, is just this thing changes itself. So for experiments, right, one thing you could do is you could measure, right? You could just make measurements, and I think I have in the notes. You could try to make measurements of actually what U of y is. So that would be just trying to probe, right, doing actual measurements along, right, taking your probe or your hot water anemometer, making measurements right above the plate, right, and then you could get some experimental velocity profile. You do a polynomial fit and you do all these techniques, and you would get, right, the types of relationships you're trying to get at. Exactly what they did. So another way you could do it is you just try to measure the boundary layer. That's kind of weird, because how would you do that? But, right, usually you would do something like this. You would set up an experiment. You say this is proportional to raised to the power A. So actually, credit is how would you actually perform this experiment. So you have a surface, a flat plate, let's say. Okay, here's U infinity. And I'm telling you, you want to actually try and measure this at many points. That's what you're trying to measure. And you can do it because, right, you know that right over here, this is all U infinity. As soon as it becomes not U infinity, I'm in the viscous part. So this is inviscid. Right, split. So you could go from top down, and then you would get that right, you would get that millimeter distance as soon as this quantity starts drastically changing. So right, let's think about us going from like down here maybe. So this would be like our y coordinate. This is U, right? So if I'm trying to measure the actual boundary layer, right, one thing I do is I could start, right, I'm starting here, and as I'm going to grow, right, it's going to go just a value and then drop down. Might not look like that, but something like that. But the thing is, like, you just need to care what that is. That would be the boundary layer at that point right there. So you could do it that way, and then pose. We know that they're always Reynolds number, right? They're always related to the Reynolds number. Before we had this with -1/2 in the laminar case. But if it's really turbulent, you just pose it like this and figure out what that constant is and what this constant is. So 2 points of data and 2 assumptions, you could get this. So that's an extra credit to devise that experiment of how would you actually figure out what A is. Just imagine you have the ability to actually take these measurements and make a little data set, pretend data set, and try to pin down what those two are. So that's one example. It's an extra credit example. I think it's fun to always devise experiments in your head. So one thing, we're going to write momentum thickness, right, non-dimensionally, right? We take out this, and then we'll have 0 to 1. And this would be, right, where this is non-dimensional velocity is going to be the velocity divided by the scale velocity. You guessed it. y divided by the x, so that's that. So all that happens is this pops out. We integrate from 0 to 1 now, and now this integral is a non-dimensional quantity. So sometimes that's actually easier to substitute in or actually just calculate. Now you can understand, since this has no dimension involved into it, if you really just make an assumption of what this function looks like, you would then get the proportionality, because this will evaluate out to just a number, and then you would have the momentum thickness is this amount of the boundary layer thickness. So it could be like, you could, after you do this calculation, you can say, oh, momentum thickness is about a third as tall as the boundary layer thickness. But we can see that hanging out. So back to those experiments, that's kind of the thing. What happened is Prandtl did a bunch of measurements with really, really turbulent flows over external flows, and he said, you know what's a really good one? I found it. This really works good for my data. Just that. Pretty simple. He had a 7th power law. So he did that, and then what you do is you plug this into there, and you will get turbulent. So that's only true if you make the assumption it looks like this. Extra credit is do that calculation. So, right, what all we've done is we've taken just these assumptions now of what the velocity profile looks like. We plug them into the momentum thickness. Now we're going to get to that shear stress, right? What is the shear stress of that? And we're going to use the momentum thickness, right? So nothing too bad. So we have to take the wall. Boom. Boom. Right, boom. But right, we already showed from the Prandtl that this is just sort of a number to the boundary layer itself, right? This was 7 over 72. So it's linearly proportional to the boundary layer thickness. That means this becomes okay. So now you see that we have this issue of, if I also want to get what the shear stress is, I need to know what the functional form of this is, and that's where that. Okay, well, I could also figure out what this thing is. Right, it could be a C1 x over r to the x raised to the half a. Not the half, right? So turbulence, you need to figure out what this a is, not the half. You need to figure it could be other things as well. Sometimes you also know what the stress is, so inversely you could actually figure out what the boundary layer is. There's an example in the book where they do it the other way. They know what this is, and they're figuring out what the boundary layer is. But I usually want to figure out what the shear stress is, because it can be hard to measure. Right, you could be directly measuring it, can be sometimes hard. So let's say you just make these measurements and you figure out what the delta is. You plug that into here, and now you can actually calculate what it is to a reasonable degree. So, and again, this r to the x, always remind yourself, it's really a function of x. Right? Wait, that's an x, not an L, not a D. It's a changing value, it's an x. So think of r as a function of x. Throw all that together and do the chain rule a couple times, and you can do this wonderful thing where you can see that then the shear stress is a function of x. Multiplication of two constants that are based on experiment, 1 minus an a. Boom. 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 Extra credit do this, but notice that the power matches. Right, power, right, this I already said was that, right, it said it looked like this. So it's just interesting to notice that whatever the Reynolds number power dependence, if you assume a power law for the boundary layer thickness, that's going to match as well. And that's just the... Okay, so that's shear stress. Bring it all back now. Remember that we want this, and I gave you the definition of that. So this is this integral. I mean, ta-da, right? Look at that. We did come up with the tau of x. And this is turbulent where we made this assumption, right? We're making this assumption of what this function looks like by experiment. We said it was this. Right? So none of this works if you don't make this assumption. If you don't make the assumption of what this looks like or the boundary layer, then you can't get what this function would be. You need to give me two pieces of information. But I can calculate this now because now it's just integration. Okay. And then you get this. After you do the calculations, it's just some number. L. This now is a full L because I've integrated from 0 to L. Okay. So again, this will also match the power. And you'll see that for all these Reynolds number dependencies, if they are power laws, turbulent or laminar, the coefficient's going to match the power, the shear is going to match the power, etc. In fact, whatever you did here, this only played nice because we assumed really a polynomial fit. But that's just one assumption. If you go back to the internal one, you'll see that there's a log wall that is really mostly true for, right? That's the most true thing for turbulent flows. So we can throw that in and get better results.